Okay, we're not done talking about indeterminate forms. So far, we have established these two indeterminate forms. And if you have the limit of a function where the function is in one of these forms, if it's a ratio and the numerator and denominator are either both approaching 0 or both approaching infinity, then of course you can apply L'Hopital's rule, Bernoulli's rule. But turns out there are other indeterminate forms that will come up. So let's make a list, and I'm going to categorize them into different, by which strategy you can use. So another indeterminate form is 0 times infinity, where you have a product of functions and one of them is approaching 0 and the other one's approaching infinity. You could also have infinity minus infinity, where it's like they're both approaching infinity, but does this mean that it's approaching 0 or is it approaching something else? What's going on? These are both indeterminate forms. You can't tell what's going on. You have no idea. But you can, in these cases, it's often possible via algebra gymnastics, you can convert to something of the form 0 over 0 or infinity over infinity. Then apply L'Hopital's rule. L'Hopital's rule only applies in these two cases. So if you find a different sort of indeterminate form, you have to convert it back to something in this form and then apply L'Hopital's rule. Okay, you could make sort of like a flow chart, like start one here, convert to this, and then do L'Hopital. Another example. Okay, so another whole category of indeterminate forms are exponential form indeterminate forms. One of them is 0 to the power 0. 0 to the power 0, if you have like one of those type of functions where it's an exponential expression where the base and the power are both functions of x, we use logarithmic differentiation to find the derivatives of those things back in chapter 3. For those type of functions, if the base and the exponent are both approaching 0, or if the base is approaching 1 and the exponent's approaching infinity, or if the base is approaching infinity and the exponent's approaching 0, those three things are all also indeterminate forms. And for those, what you can do is basically approach them the same way that we approached logarithmic differentiation, by starting by doing a logarithm. So we're going to apply logarithms, usually to convert to 0 times infinity. Then convert your 0 times infinity to 0 over 0 or infinity over infinity, and then apply L'Hopital. So it really is like a flow chart. We've got, if it's in one of these formats, you can usually convert it to one of these, which you can then convert back to one of these, and then you can apply L'Hopital. But you always have to convert back to one of these forms before you do that. So, okay, those are all the types of indeterminate forms that we're going to be working with. So, let's first start. We've already addressed these two cases. Those are the easy ones. Let's first start with a 0 times infinity case. Okay, so we're going to go to this one. Now, if you have two functions multiplied together, and one is approaching 0 and the other is approaching infinity, here's what you can do. You can apply a kind of an algebra trick, which is f times g is the same as f divided by 1 over g, which in turn is also the same as g divided by 1 over f. Basically, you're going to take one of these two functions and do two things. You're going to reciprocate it and put it in the denominator, which are two operations that essentially are inverses of each other. So, like, dividing by something is the same as multiplying by its reciprocal. So multiplying by something is the same as dividing by its reciprocal. I think, yeah, what I just said is exactly correct. Multiplying by something is the same as dividing by its reciprocal. So that's what we're doing here. And that's going to help us take this from basically a product into a quotient, which hopefully will be in one of these two forms. It should be in one of these two formats. So let's do an example. Let's call this example. I ran out. I forgot what number we're on, so I'm not going to do numbering. We're going to take the limit as x approaches negative infinity of x times e to the x. All right, x is approaching negative infinity. E to the x is approaching 0. Let's write that. I'm going to put that in purple here. This one is approaching negative infinity, and this one is approaching 0. So this is a 0 times infinity indeterminate form, okay? I know that one of these is negative infinity, but that honestly doesn't matter. In this case, at least, it doesn't matter. It would matter in this one because you have to have the subtraction there. So if that was addition instead of subtraction, it wouldn't be indeterminate. But in this one, and also in these, by the way, like in these two indeterminate forms and these ones, it doesn't really matter if it's positive or negative infinity. It's basically the same thing. So that's indeterminate. So now what we're going to do is we're going to attempt to solve this by taking one of these two functions and reciprocating it and then putting it in the denominator. So let's try this. Let's try converting it to what should I do first? I'm gonna try this one first. There's two options here, and I'll write them both down, and then we can decide which one to try. Well, I'm gonna do both actually. So here's one option where we take the first function, reciprocate that, and put it in the denominator. So this is now in the format e to the x is approaching 0, and x to the negative 1, as x approaches negative infinity, this is going to be approaching 0 as well. So that is a 0 over 0 format. I could apply L'Hopital's rule to that one. The other possibility is to reciprocate the other function. So that was reciprocating the x. Then you could also reciprocate e to the x and get the limit as x approaches negative infinity of x over e to the negative x. Okay, so that's reciprocating the e to the x and putting it down there. X is approaching negative infinity. E to the negative x as x approaches negative infinity. That you flip the negatives around, and you'd be like getting e to the power infinity. That's approaching infinity as well. So this is an infinity over infinity format. We could apply L'Hopital's rule to that one as well. So the point is, when you have a product, one of them is 0 and one of them is infinity, you can flip it one way and get 0 over 0, or you can flip it another way and get infinity over infinity, and either of these should work, hypothetically. In reality, in practice, like sometimes only one of them works and the other one doesn't. So let's try both of them and see what happens. We're gonna do A and B. Okay, so A, the limit as x approaches negative infinity, e to the x over x to the negative 1. Apply L'Hopital's rule, because that's 0 over 0. Okay, the derivative of e to the x is itself. The derivative of x to the negative 1 is negative x to the negative 2, right? Okay, the numerator is approaching 0. The denominator is also approaching 0. So that's still 0 over 0. So we could apply L'Hopital's rule again. Okay, since it's still an indeterminate form that we can use L'Hopital on, let's use L'Hopital again. The derivative of the numerator is e to the x. The derivative of the denominator is going to be positive 2 x to the power negative 3. That's still 0 over 0. Let's try it again. E to the x over negative 6 x to the negative 4. This isn't helping. ... This is not helping, right? What's happening here is every time I differentiate the numerator, I get the same thing. It's always e to the x. And every time I differentiate this denominator, its power goes down. And if it starts at negative 1, it's actually going down negative 2, negative 3, negative 4. Those denominators are always giving me, those are always approaching 0. That didn't work. This is just going to go on forever, and it's never going to get any simpler. It's never actually going to become something I can find the limit of. So never mind. Fail. B, let's try it the other way. Okay, the other possibility was to do this reciprocating trick with the other function. So that one is x over e to the negative x. And now that's infinity over infinity. If I apply L'Hopital rule to that, I get 1, the derivative of x is 1, divided by negative e to the negative x. That would be applying the chain rule, a little chain rule there to get the negative 1. Okay, that's promising. because differentiating x gave me 1, right? So now the numerator is approaching 1. Now what's my denominator approaching? Oh, I really want to do like a u substitution. Let's let u equal negative x. As x is approaching negative infinity, since u is just the opposite, it's going to be approaching positive infinity. So I'm going to write this as the limit as u approaches positive infinity of, I'll put the negative in the numerator, negative 1 over e to the u. And then that, let's bring it down here. Okay, that, I'm actually going to rewrite this one more time. I'm going to put that e to the u back up in the numerator again. And let's take that negative and pull it out front. And write it like that. So the negative came out front, and then the e to the u has gone up into the numerator, and now it's e to the negative u, right? Like the reciprocal of e to the u is e to the negative u. Now this corresponds directly to one of our rules. E to the negative u is going to look like that. If this is our u-axis, if this is our y-axis here, e to the negative u is the exponential decay function, so it goes down. And as u approaches positive infinity over here, that is approaching 0, right? So that one is going to be 0. So what happened? We were actually able to show that this limit here equals 0, right? And one of the two possible manipulations did not help, right? Because it gave us this infinite sequence of progressively worse and worse and worse functions, right? With the denominator power going down and down and down forever. That failed. But the other possible manipulation, flipping it around the other way, that, after applying L'Hopital's rule just one time, led us to something that we could manipulate into a format we could figure out. So that worked. All right, that'll do it for this example. I know that was kind of long. Let's see what's next.